Thank you very much. So today I'll be talking about structure function. This is a topic related to scattering, ultrasonic scattering in tissue. So acoustic scattering in soft tissue is related to the properties of individual scatterers. This is modeled by a form factor. It is also influenced by the spatial distribution of scatterers. This is modeled by a structure function. The total scattered power is the sum of scattered power from individual scatterers multiplied by the structure function. For sparse medium, where the particles have low concentration, the scatterers are spatially uncorrelated, so we can assume structure function is 1. For dense medium, however, the scatterers are spatially correlated because they are close to each other. The frequency-dependent structure function we have for the dense medium. We're going to study structure function from theory and from ultrasonic measurement and also histology. The goal is to improve the understanding of scattering in tissues and to improve scattering models for quantitative ultrasound tissue characterization. We'll begin with the theory. Here is a comparison between monodisperse and polydisperse models. Monodisperse models means that the scatterers or the spheres are assumed to be identical in size. Polydisperse models assume that the spheres are polydisperse in size. We assume a gamma distribution. Oops. So this is a comparison between monodisperse and polydisperse models for the structure function plotted as a function of Ka. And we plot the 1% volume fraction. This is a low concentration case. The structure function is close to 1, and monodisperse and polydisperse have similar results. When you see a 20% volume fraction, the structure function is significantly different from unity. And as we increase this volume fraction, we see a bigger peak, and also we see a difference between monodisperse versus polydisperse, and the 70%. There are two ways of estimating structure function. First is Fourier transform of scatter positions. From this equation, we'll be able to estimate structure function from histology because we can identify the scatter positions from histology. The second estimation is ultrasonic estimation. According to the total power is the sum of individual scatterers multiplied by structure function. So we have the backscatter coefficient proportional to the number density and the structure function. If we have two medium or two phantoms have the same scatterers but just different concentrations, then we can estimate the backscatter coefficient for the two concentrations. And then if we assume that the low concentration case has a unity structure function, then we'll be able to estimate the structure function for the high density case. For the experiment, we constructed biophantoms by putting known number of cells in a mixture of bovine plasma and thrombin. We studied two cell concentrations, a high concentration that mimics the situation of dense tissue, and a low concentration for which the scatterers may be assumed to be uncorrelated. We have unit structure function. We estimate backscatter coefficient using single element transducers and we estimate structure function from the backscatter coefficient results. We also process the biophantoms after scanning, and we repeat the experiment on 3 cell lines, and we also have multiple realization for each cell line. Here is the result for the backscatter coefficient for one of the cell lines, the MAC cell lines. The red and the blue are different concentrations. So clearly you see that the two colors have significantly different frequency dependency, which suggests that the structure function is not unity for the higher concentration case. We obtained similar results for the other cell lines, which I'm not going to show here. We estimated the structure function from the backscatter coefficient for the 3 cell lines. The structure function is plotted as a function of frequency. The 3 curves have similar behaviors in the sense that they have lower than unity values at lower frequencies, and they have a peak. The peak locations are different for different cell lines. And you can see for the green one, the peak is the lowest, corresponding to highest cell radius. Now the question is, are those acoustically estimated structure functions indeed caused by the scanner position distribution? We propose to calculate the structure function from histology to answer this question. So the procedure for calculating structure function from histology is as follows. We digitize H&E scan histological slides, and we determine the scanner positions, and we perform a 2D Fourier transform on the scanner positions, and calculate the radial average of the normalized square modulus of the 2D Fourier transform to yield the structure function independently from ultrasound measurement. This is a digitized H&E image, the cells and the nucleus. Magnification is 40x, resolution is about 6 pixels per micron. We determine the positions in the yellow dots. Then here's the plot of the positions. And we do a circular windowing and then calculate the normalized squared modulus of Fourier transform. You see some kind of a circular symmetry on this Fourier transform. Then we get the result for the structure function from histology for different cell lines. Similar to the ultrasonic measurement, we see a lower than unity structure function here, and then a peak around here. So finally, we compare the theory, ultrasound measurement, and histology. For the CHO cell line, what is plotted is the structure function versus frequency. We have acoustically estimated in dashed line, and we have histologically estimated in the dark, solid dark line, and then we fit the histologically estimated curve to polydisperse theory. And this is what you see in red. Then we do the same thing for MAD, another cell line, and third cell line, 41. What we have seen so far with the 3 cell lines are that they have similar frequency dependent behavior, but their magnitudes are not in good agreement. The positions of the peak are in good agreement, actually. Finally, we also compared the cell radii we looked at the ground truth cell radius, and we also fit the structure function estimated from histology to a model, and we fit the model to the ultrasound result. As you can see, the ground truth cell radius is similar to the model fit, both to histology and to ultrasound for 3 cell lines. So to conclude, we found that good agreement in frequency dependence for the structure function curve estimated from histology and from ultrasound. The agreement in magnitude is not as good. This is probably because that we use the 2D slice instead of 3D slice. So we're currently studying the 3D case from using 3 approaches. We study the 3D case in theory and in simulation, and also in 3D histology. But this is not presented here. It's still undergoing. From the result, we see the structure, the scatter position distribution has a significant effect on scattering, and the acoustically estimated structure function is related to histology and can yield useful information on tissue microstructure.